Right, so this is question 10. Dorothy and Harold push a wheelbarrow of mass 20 kilograms. They both push in the direction of motion. The wheelbarrow moves 10 meters from rest on a straight horizontal path. Dorothy applies a force of 90 newtons. Harold applies a force of 90 newtons for the first 3 meters, then reduces the force to 80 newtons for the remaining 7 meters. The resistance to motion is 170 newtons throughout. Find the time taken for the wheelbarrow to move the 10 meters. And there's 9 marks for this. This is going to be a bit of a biggie. Right, so it's a sort of mechanics question, and you can see forces and there's some sort of motion going on. So this is pretty much the only equation you know that involves forces and motion. Motion's in the acceleration there. And if there's constant acceleration, and there will be constant acceleration if m is constant and the forces are constant, then you can use the Suvat equations. Now you might be thinking, well, the forces aren't constant because it says about how Harold's force changes. But for the first 3 meters, the forces are fixed, so you've got some constant acceleration for the first 3 meters. And then for the remaining 7 meters, the forces are fixed, so there's some constant acceleration there. So you can use Suvat, but you've got to treat these two sections of motion separately. So let's have ourselves a little diagram. There's the 3 meters, there's the 7 meters. I'm just going to draw a line down there to distinguish between them. So in both scenarios, we've got a 20 kilogram mass. Okay. In the first 3 meter scenario, they're both pulling with 90 newtons. A change of pen is in order. Bear with me. Okay, I'm back. So, you can't read that very well. Let's try this. 90 newtons. And that's 90 newtons. We've got two 90 newtons forces. Can't even read the 20. So that's 20 kilograms. Okay. And there is a resistance of 170 newtons. So that's what the forces look like in the 3 meter section. And over in the 7 meter section, we've got 20 kilograms, we've got 90 newtons by Dorothy, and then we've got 80 newtons by Harold. And that's 170 newtons. Now, I've just realised something there, that over here the forces cancel each other out. Okay? And if the forces cancel each other out, it's either not moving at all, or it's moving with constant speed. Because there'll be zero acceleration there. It's in equilibrium is the word that I'm failing to use. We've got equilibrium on this side. So we're travelling at a constant speed. Over on this side, these two forces are bigger than that one, so it's going to be accelerating. So let's work out that acceleration. We're going to do F equals ma, and we're going to do it towards the right hand side. Well, the rightwards forces are 180 newtons, minus the leftwards force of 170. That is the resultant force to the right on this section. And that's what the F stands for, resultant force. The mass is 20, and then I've got times by A. So we've got 10 equals 20A, so we've got a half. So we know the acceleration for those first 3 seconds. Does it start from rest? Yes, it does. The wheelbarrow moves 10 meters from rest. So, and we're after the total time. So I'm going to work out the time taken in this section. And I'm then going to work out the time taken in this section. So I'm using Suvat now with A equals a half. We know that U is 0. We want to know what T is. We know that A is a half. Okay, well, and we know that in that time it travels 3 meters. So we're going to be using S equals ut plus a half at squared. We're going to substitute everything we know here into this. U is 0, so all of that is 0. So we get 3 equals 1/4 t squared. That means t squared equals 12. Okay, if we times both sides by 4. So t is the square root of 12. And it's going to be plus because we're kind of travelling forwards in time. Alright, I wasn't really expecting a square root, but we'll live with that. It's just a number. Now we need to work out how long this takes. We're travelling 7 meters at a constant speed. If it's constant speed, you can use speed equals distance over time. Get time. And we know the distance is 7. We're trying to get the time. We need to know what that constant speed is. Well, the constant speed for this 7 meters is whatever it finishes the 3 meters with. So we've got to go back to this side and work out what V is. You know, here. What is V using this information? And at this point you can use any of the SUVAT formulae with V in because you've kind of got a bit of everything now. But it's best to use the one without T in because if T's wrong, V's going to be wrong. So I'm going to find V when T equals 3 seconds. I'm going to be using V squared equals U squared plus 2AS. So V squared equals 0 squared plus 2 lots of a half times by 3. V squared equals, that's 0, 2 lots of a half is 1, that times by 3 is 3. So it's another square root, it's root 3. Okay, so let's work out the time taken for the final 7 meters. Okay. It's got, I'm using speed is distance over time again. Okay, in fact, if you rearrange this, time equals distance over speed. So time equals 7 divided by root 3. Okay, so the final answer for these glorious 9 marks, the total time is 7 over root 3 plus root 12. Okay, well, this is a calculator exam, so we don't need to worry about rationalising the denominator. Oh, my calculator's in a silly old mode here. Forget how to do this. Let's clear it all. Best way. Right. 7 over root 3 plus root 12. You can't see this, can you? Oh, that's gone wrong. Let's try it again. I'm having a nightmare. 7 over root 3 plus root 12. Is that number there? I can't see that either. That's 13 root 3 over 3 seconds. And for all you decimal fans out there, that is 7.5 seconds. 0.51 seconds. Okay, so there's final answer for the glorious 9 marks. Okay, let's have a look at the next question. Oh, I can't see it. Move that down a bit. Oh, it's a long question. This is the last question. We'll be pleased about that. So, here we go. Question 11. This is for quite a lot of marks as well. Chung wishes to model the fuel consumption of a car. He tries the quadratic model. Y equals A V minus B squared plus C, where Y is the fuel needed in litres per 100 kilometres and V is the speed in kilometres per hour. So these two are the variables. That's fuel and that's speed. We'll be happy with V being speed, but we'll have to try and remember that Y means fuel, and we're going to need to try and remember that it's litres per 100 kilometre. Travelling as a passenger, he notices that the minimum fuel consumption displayed on the dashboard is 10 litres per 100 kilometres and occurs at 80 kilometres per hour. Now it said minimum there, so it might be something to do with stationary points. Minimum fuel is 10 litres per 100 kilometres. So the minimum Y is 10 then. And this happens when the velocity is 80. Okay. I'm not needing to write the per 100 kilometres because that's part of the unit of fuel anyway in this situation. So the minimum fuel, Y, is 10. I mean, I like to write Y min. So Y minimum is 10, and that happens when V is 80. Write down the values of B and C for which Chung's model fits this information. Okay, well, I've just realised that rather than doing differentiation and stationary points, that this is written in the completed the square form. Okay, so when you've got completed the square form, you can suss out where the minimum is, can't you? Okay, I've forgotten how, but I'll get there in the end. Well, assuming V can be anything you like, the minimum value of something squared is 0, isn't it? The minimum value of something squared is 0. If you times that by A, that'll still be 0. So the minimum value will be C. So Y min is C. That means 10 is C. Okay? And then let's just go back to that a second to try and write down B. Remember I said the minimum value of something squared is 0. Well, the minimum value occurs when V is 80. So what would B need to be with this 80 here to make this 0 squared? B would need to be 80 as well. Okay, that's how you answer that question using the write down method that the question talks about. You can do it with stationary points, but that's not the way this question wants you to answer it. Just having a bit of tea there. At 30 kilometers an hour, the fuel consumption, at 30 kilometers an hour, the fuel consumption displayed is 20 litres per 100 kilometers. So I'm going to write that down. When V equals 30, okay, the fuel consumption Y is 12 litres per 100 kilometers. Find the value of A for which Chung's model fits this equation. So I'm going to rewrite Chung's model out and I'm going to put the values of B and C in. There it is. And now I've got to find the value of A that fits this information as well as the previous information. So all I can do is substitute these numbers in. And then I created myself an equation with the unknown A in it. So I'm going to take 10 from both sides. 30 minus 80 is minus 50. Okay, so it's 2 over minus 50 squared. Minus 50 squared is 2,500. So A is that number there. Okay, so decimal fans, it's that, isn't it? Yeah, it refuses to tell me. Yep, it's that. Oh, I'm not sure whether that's the right unit, by the way. No, it's not the right unit because speed is in kilometers per hour, so this will be kilometers per hour squared. What a lovely acceleration that is. I suspect they're not too worried about the unit in this question. It said find the value of A, and the value is the number. Right, part 3. Use this model to predict the fuel consumption at 110 kilometers. So that's what is Y when V equals 110. Okay, so we're going to use the model, and I can't bear to write that decimal, I'm sorry. Let's use the cancelled down version of A. So there it is there, and I've got to substitute in Y is 110. Sorry, V is 110. So there it is there. So what are we going to get? 30 squared. 30 squared is 900, I think. So we get this 30 squared is 900, divide by 1250, that plus 10, 10.72. Oops. And what is this? This is a fuel consumption, isn't it? Yes, it is. And the fuel consumption is litres per 100 kilometres. A horrid unit that is. But there it is nonetheless. Right, I'm going to have to go to another piece of paper. So I'm just going to pause there in case you need to pause and look at some of this again. Right, you can always find it, of course. Part 4. Sketch the graph of the model for speeds between 30 and 110. So let's just put this down again. That'll be the nicest graph to sketch. Remember, there is a minimum of y min equals 10 when v equals 80. We know that information. What other information do we know? We know when y equals 12, v is 30. We know that when y equals 10.72, v equals 110. We found out all this information, which should help us sketch the graph. So they're all positive y values by the look of it. So when I'm going to put y on the y-axis, strangely enough. So when v is 30, the lowest value, we get 12. Okay, is that the minimum one? No, the minimum occurs at 80. So we're going to have 80 and we're going to have 110. And at 110 we get 10.72. Here it's 10. The minimum is there. This one, that will be 12. It's not the best sketch in the world, of course, and then at 110 we'll have 2.72. So we're going to have something like this. Okay, not the best thing, but it is only a sketch. I've got the minimum on there. You know, I've labelled the axes. I think that'll do, to be honest. They're looking to see if you include all the information the question's given you. Right, later in the journey, Chung notices that the fuel consumption of 12 litres per 100 kilometre is displayed at 30 kilometers an hour and also at 110. So we had that there, but he actually spots that this should have been 12. Okay. The minimum fuel consumption still occurs at 80. Give a reason why a quadratic model cannot fit all the information that Chung has found. Well, it wouldn't be symmetrical as my first thought, because you've still got this here, that still exists. Alright, this here at 110 would have to change to there. So it's going to look, you know, something like this now. And you've lost that symmetry. So you could write that. You could say all quadratic graphs have symmetry in a vertical line. It could even be a real spot and say through the minimum. This change would cause a non-symmetrical graph. I'm writing quite a lot here. To be honest, if you said there is no symmetry, that would and quadratics always have symmetry, that would probably do. Right, that's the end of question 11. I think that might be it. Yes, it is, because it's scrolled round to the first question. So that's done.